Hey ladies and gentlemen, welcome to another edition of VRM Explanations. Today's article is on high power MOSFETs. Alright, now the high power MOSFETs today we're going to talk about are the IR3550, which are rated 60 amps, PH7030AL, which are LF pack, and then 4921N, which is power pack. IR3550 are power stages. Alright, so when we get down to business, I'm going to go over their graphs, and I'm going to show you how to really go through a data sheet and go through it. So let's start off not with the best, the IR3550. Let's start off with 7030AL. Now first we're gonna rate MOSFETs on two criteria. Number one is 90% efficiency. What is their current output at 90% efficiency? Second of all, what is their power output at 11 watts? That is thermal dissipation, power dissipation. All of these have statistics for those two and only those two. All of these voltages that they switch at are all around 1.2 volts, as well as many of their other considerations are the same. However, one thing that we can derive from all their data sheets is their power as well as their efficiency. Now, that's kind of hard to do, especially with how these are done nowadays. But we're going to get down to it, and actually some of them we can't figure out their efficiency, especially these two. We cannot figure out efficiency, so it is NA. Does not apply. Alright? Because power stages, integrated power stages, are what really efficiency is all get up and hype about. Except efficiency is telling for different things in the same range. But these two, let's go over first. This power dissipation is a huge limiter. How much heat can something give out before it gives out, and how much current at that heat will it output? So first of all, let's do 7030AL. Now I've printed these in big fonts, and I've mixed some of them together. These are 7030AL MOSFET characteristics. These MOSFETs are used on many ASUS boards as well as some ASRock boards. 7030AL is used on the Maximus 5 Genie, the Maximus 5 Extreme, P8Z77 Pro, the Deluxe, all the high-end ASUS boards. Z77 use this. Alright? They all use this as their high side FET. Now remember from the other previous, the high side FET is the limiter of current when it comes to MOSFETs, because the high side FET is connecting to 12 volt or 5 volt to the inductor, and then the inductor limits. But first we're limited at the high side MOSFET. So it does not matter what your inductor can do unless your MOSFET can do it too. So let's go over the MOSFET. Here we see some very direct terms, alright? 68 amps at 62.5 watts. Now 68 amps sounds great, right? Can this high side FET really do 68 amps? Then it would be better than IR3550. However, no, it cannot do 68 amps. It does 68 amps at 62.5 watts. That's basically, it can output 68 amps when you cool it as if it's a CPU. Alright? That's not going to happen. Of course, it's not going to happen. Alright? Let me just tell you that. And I'll go over why. So, that's kind of telling. However, it also has some graphs attached to it that are even more telling. These two numbers, 68 amps, and we have total power dissipation as well as total continuous drain current. Alright, and we have to use these two, 62.5 watts and 68 amps, in these equations to find out exactly what we're looking for. So first of all, let's go over power dissipation, okay, at 11 watts. This is power dissipation as a normalized function. The equation is P dir is what's on this end, equals P total divided by P total at 25C. P total at 25C is this, 62.5 times 100. So what are we going to compare at, right? I mean, we don't really know. Well, P total I'm looking for is 11 watts. So 11 divided by 62.5 times 100 will give me a temperature on this graph. And that's going to be important because then we're going to use this temperature and go over to the current graph at the same temperature and we're going to rate it. Alright, because 25C is the ambient temperature. 11 divided by 62.5 times 100 equals 17.6. Where's 17.6 here? This is 20. This would be 10. So 17 would be right up here, right here. Alright, this little dot right here. So this would be 125 right here. This would be 150. So we're looking at about 130. So we'll be nice and say 130C. We move over to this graph. We find the exact same location. We go up and we hit this graph right here. We're right around 40. I'll give this, because this will be 60 right here. I'm going to give this, and the 50 will be in the middle, 42. 42 will equal I dir percent. So 42, and remember this equation is basically the same as this one, which is I dir equals ID, which is actual current drain, divided by ID at 25C, which equals 68.68 amps times 100. So we're going to put, right, 42 equals X, we're solving for X, over 68 times 100. Right? Exactly, right? Alright, so we're going to divide by 100, so that would be 0.42 times 68. That equals actual X equals 28.56 amps at 11 watts. Why 11 watts? 11 watts because IR3550 is rated 60 amps at 11 watts. 7030AL in the same conditions is only rated 28.56 amps. That's less than half IR3550 output. Even though it says 68 amps, it's bullshitting you. Don't let it mess with you, alright? It's falsified. Alright? It's not really falsified, it's just misrepresented because that can never happen. Now there's no efficiency curve for this readily available, so we won't mess with that. But that's how I showed you how to go take these two graphs. This is for current normalized and this is for power normalized. If you want to find the current at a certain power, you input into this equation, you find it on the graph, convey that same temperature over here, and take that and do it. If we did the same thing with 62.5 watts, we would get 68 amp output. That's how that kind of stuff works, alright? That's how it works, and that's how manufacturers can go and actually calculate the true output of certain MOSFETs and not their maximum possible at 62.5 watts. I don't even think they can cool one at 62.5 watts because it's like the size of a pin, alright? So that's just BS, so that's done. Let's take a look at some other MOSFETs. This 4921N MOSFET, this is found on many like a UD3H uses this from Gigabyte Z77. This is, it says on the data sheet, 58.5 amps. That, however, is at 38.5 watts. So this does 58.5 amps at 38.5 watts. That's still undoable, right? Because we're only dealing with 11 watts. So we have to convert this down. However, it gives us a lot of other interesting things. 13.8 amps at 2.4 watts. That's reasonable. 22.4 amps at 5.61 watts. That's looking really good. 8.8 amps at 0.87 watts. That's decent too. We can do that. And then 58.5 at 8. You see all these graphs are exponential. So what do? What I do is I make my own graph. I plot these coordinates, the current and the wattage. So watts are on this side and current is on this side. Then I'm left, I did this in Excel, you're left with an exponential line if you do a linear curve fit line, alright? And it's exponential, and it'll give us the actual output value. So you have 7, that gives you this equation. So how does one solve y equals 0.7661 e to the 0.0699x? How does one solve for that? E is a natural constant. E equals 2.71. That's it. So we got to use a calculator and we use an ln function. Now if you're not good with algebra, I'm going to do this and show you the steps I use. First of all, we're solving for something on the y-axis, 11 watts. So 11, to get the x, which is the current, which is all the way up here in the exponent, you have to do some math. So 0.7661 e 0.0699x, right? Right. So first we do is we get rid of this 7 point whatever. So you divide by 0.7661, right? So 11 divided by 0.7661, that equals 14.358 equals e to the 0.669699x, 0.0699x, alright? So what do you do when you have e? You ln both sides. ln is the natural logarithm. So ln this, and then when you do ln, this is just done and the exponent comes down. So that equals 0.0699x is ln of my answer equals 2.664. Now this is an easy solvable equation, right? So we divide here by 0.0699 and we get an output. X equals 38.116 amps. Okay? That gives you your answer here. 38.116 amps. Alright? You see it's more than 7030 AOL, but still basically just a little bit more than half of what IR3550 will do. And I'll show you the IR3550 graph. Now, I want to remind you, all these data sheets are easily found Google by just Googling 7030AL or Googling 4921N or Googling SIC780CD, which is actually, this is actually a 50 amp driver MOSFET. Alright? You can just Google them and you can find this exact information. You can do this all at home. So now we found out that that MOSFET is rated 58 amps at 38 watts, but at 11 watts it's only rated 38 amps. Alright, and you see that was an exponential graph with the line going really high here. Now when this line goes higher, that means that the watts are going to get exponentially larger as the current gets higher. So even 58 would be much more than 59 would be much more than 58. So in real life it might actually be a little worse than that. So current output, this line might not, this line is not sloping much. That's only because we had 4 data points, right? We had data point here, 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 and here. That's all I had to work with, and thus that's where I get this line. It's following the exponential curve, which is probably correct. However, its current would actually be higher if we just followed this line in a linear progression, which we're not doing. Its current would be probably in whatever's, but these are all exponential. None of them are linear, and you'll see that by when I show you actual current graphs from the driver MOSFETs and the power stage. So now we're done with these two, right? Let's take a look at this. This is a brand new product, all right? This product is from where is that thing? This product, SIC780CD, is a no. These two go to this. This is a 50 amp driver MOSFET from Vishay. Okay, so you can just Google this and get that. I've done the same thing where I graphed it, but the graph is already given me here. I just took the points and I made my own curve because I need to extend the graph and I needed this equation. I need this equation so I can plug in my own variables and find them. So we see here power loss. Now look, this 50 amp driver MOS doesn't even have 50 amp. This is 35 amps right here. 35 right here. It's crazy or not. It's not giving you any values at 50 amps. What is that about, right? What the hell is that about? Even on its efficiency curve. Let's figure out the efficiency first. That's easy. 90 is right here. Now all of these efficiencies, they go up and then they come back down. We catch them when they come back down because that's what's important to us. So 90% is right here, and we're always going to go 300 kilohertz because that's what all these are rated at. As you go higher in the kilohertz, your efficiency lowers and your power loss increases. So we're just dealing with 300. That's 20 amps. 20 amps at 90%. That's crap, right? If you're going to do 90%, which is what you're going to do, then you got to do that. 20 amps here is only 2.5 watts, which is good, right? That's excellent. Anyway, so I've transcribed this graph into here. You can check my results if you care. You take a nice picture of that if you like, and they're the same basically. So I find my equation here for SIC780CD. Again, I have y, that's not a y, that's a 7. Y equals 0.4544 E0.0839X. Alright? Remember, 11 watts once again. This is the same thing. Watts versus current. So 11 divided by 0.4544 equals 24.2. Oh, and I'm going to take the natural log of that. So then I get 3.1867. It's a large point. Equals 0.0839x. Now we divide 3 point whatever by 0.839. I haven't done this before. 37. X equals 37.98. So right below 4921N. Interesting, huh? Very interesting. Driver MOSFET efficiency is not that great, but its 11 watt power output is almost as high as 7921N, and this is a 50 amp driver MOSFET. That's what it says on the data sheet. Look it up. This is a 35 amp one, which is most commonly used. I have not seen this used on a motherboard yet, so not used. But it seems to do okay, right? 11 watts, it can do 98. That's pretty good, right? That's pretty good, right? Anyways, so now we have our numbers from there. We see once again it's not a 50 amp piece. I'm saying 11 watts because 11 watts is where that's rated 60 amps. IR3550 is rated 60 amps at 11 watts. And I forget the efficiency, but I think it's like 50 amps at 90%, which is pretty damn good. So now we're done with the 50 amp driver MOSFET. Now we go to the 35 amp driver MOSFET. Alright, 35 amp driver MOSFET has two graphs. I separated them. And I made my own graph once again with another slope and with another equation. So here we see that actually this seems to have better product at 300 kilohertz, 90% efficiency. We're about 15, I'd say 18 amps. So when it comes to efficiency, 35 amps is just a little lower. Now, don't these curves look a lot alike? Like this equation on this curve look a lot alike like the other one? It does. You want to know why? You really want to know why? Because I think that Vishay just took the 35 amp, added some more metal to it, and made it a 50 amp. Because as you'll see, its wattage is actually higher than the 50 amp driver MOSFET, or the same. And that's embarrassing because they're cheating their buyers. And that's why no one's used them yet. Because the 35 amp basically does the same. Yeah, man. It's the same. Anyway, so let's take our equation and do this. You can go look this up and do this all yourself. And you'll have the same exact results as me. Believe me. Alright, so we have y equals 0.3085e 0.0824. What was the last one? The last one was y equals 0.4544e 0.0839. Alright, so this was 50 amp. The 50 amp. And this is the 35 amp driver MOS. Now they're not really 50 amp and 35 amp as we've seen. Alright, so let's do our equation. 11 divided by 0.3085. This will give us 35.65, and we're going to do the ln of that. And then we're going to get 3.5739. And then remember, we're going to divide by this number, or this one. This is not what we're using right now. We're using this. So we're going to divide by 0.0824. Remember, this was the last one we did. Wow, it is higher. This equals 43.37 amps. That's the highest yet, except for IR. What does that mean? That means that 35 amp driver MOSFETs are pretty dead on. Of course, you're usually going to be only working at 90% efficiency and not lower, or else your thermals go way too high. but that's awesome. That's awesome, and I'm getting better and better, right? However, here we come to IR3550. Don't need any graphs. Everything is so simple with this that it's just freaking amazing. They don't do normalize this, normalize that. Why? Because their numbers are so good, they don't need to trick any potential buyers into buying them. They have proven themselves the best, and now I'm going to mathematically theorize they're the best that's been on a motherboard. So power losses on this side with this black line. Efficiency is this curve right here. Right here, right? Just like a normal exponential, just like we saw before, and an efficiency curve just like we saw before. 90% efficiency is right here. This 90 is right there. That's right at 50, 51. Do you see that shit? 50, 51. Let me take this up to you so you can see a little better. Right? Take a glance. Also do a power outage. 11 watts is what? 60. Do you see that? 60. 60! 60! That's 60, man. 60 watts and 51 amps at 90%. Do you see that? Do you see that? Do you see which one is the best? Do you see that? Is that simple? 60, 28.5, 38.1, 37.98, 43.37, amperage, efficiency. At the same power output, same heat, IR3550 gets the gold at 60 amp. Okay? 7030AL at 30 amp will be nice. We'll round. 4921N 38 amp. SIC 780 38 amp. SIC 769 43 amp. Do you see? This is the gold. Right? This is the silver. Okay? These two are the bronzes. And this is an honorable mention. These are all extremely high performance components though, alright? This is extremely high performance. As you've seen, 7030AL on the high-end Asus boards can easily grab LN2 operating because I think 10 amps to 11 watts per phase is something that is doable, you know? Something that is doable in maximum outputs. These are the maximum outputs. These are the maximum outputs. These are basically the best also ever used. Oh, a direct FET would be close to IR3550. Very close. But I don't have any used on current boards, just these, except for this. This is not used on anything, so that would be the bronze. You see what I'm getting at though, right? But in efficiency, the IR3550 is top, of course. However, then comes the 50 amp driver MOS. I'm not going to write that, I'm going to write its name. SIC 780, and then SIC 769. You see that? That's the gold, the silver, and the bronze. Alright, thank you for watching today. I also have one more thing to say. I heard rumors that Asus is going to start using the IR3550. However, Asus always restamps their product, alright? That to me is unacceptable. People need to know exactly what they have on their motherboard, or else it's just fraud, alright? Well, not really fraud, but whatever. Alright, IR3550 compared to its other derivatives, there's the IR3551, which is 50 amps, as well as the IR3553, which is 40 amps. You will find this on X79 GB boards for DDR, as well as VCCIO, which is also IMC voltage, and VCCSA, which is system agent. These will be used on X79 for that. At least for I/O and DDR. Some VCCSA don't use them. Also, VCSA on the new UP boards use this. So XMA9, VCSA, and that use this. And then for DDR and VCIO, actually, they only use them for this. All VCSA are either this or MOSFETs like this, usually IR derivatives. So these are the best MOSFETs to ever set foot on a motherboard, except for DirectFET is not included, of course. God embrace DirectFETs. They're great too. They're excellent. Anyways, so we're talking about this stuff. So there's a size difference. So when you see it on your motherboard, this will be a rectangle, right? Then you get a little bit fatter, and it's not quite a square. Actually, I drew this pretty bad. This should be even shorter. Then it's IR3551. When it's a big square, a fat square, then it's IR3550. And you can actually measure them. I believe online they have measurements for the dimensions, and you can use Photoshop. If you see Asus board on a review, take a measurement of the board's width, and then scale it down your measurement ruler to see what's what. So now that everyone's seen this, I want to say thank you for watching SynHardware.com. I hope other motherboard manufacturers start embracing IR3550. Till now, EVGA has on their current, they use 7 of them on their Z77 FTW. Gigabyte has on all their UP boards, which are brand new and excellent, and no one else has yet. Anyways, have a nice day, and thank you for watching another edition of VRM Explanations, MOSFET Olympics. Bye-bye.